Section 7.1, exploring exponential models. We're going to look at exponential growth and decay today. It's kind of like a sciencey kind of thing, but there are other types of things that we'll look at as well. You might want to write down this part right here. The things that are really important are the things that follow. What can the numbers be? What can the numbers not be? So I want you to write that down. An exponential function, y equals ab to the x. That's kind of what it looks like. A can't be 0 because then you just have the equation y equals 0, which doesn't make sense. That's just a line. Exponential functions are more like a curve, not a line. The base of the number that has the exponent has to be bigger than 0, so that part won't be negative and it won't be 0 either. And then the number can't be 1 either, because if you put a 1 in there, it kind of brings this back to being a line, which it's not. So you're kind of looking for the numbers that make this thing look like a curve, because that's what it is. So we're going to graph one so that you do know what it looks like right now. So when we're looking at this one, the 2 is actually the b in your equation. There is a 1 ahead of it if you want to think of it that way. So the a part is not 0 because it's 1. The b part is not 1, and the b is bigger than 0. So that's kind of what you're looking for. And it does look like something that has an exponent. So we're just going to do, for the sake of this one, a bunch of numbers just plugged in. Okay, so I'm just going to do a little XY table for this one until you kind of know what it looks like. So I'm going to go with these. Okay, just so we can kind of see what it is doing. It didn't say anything about the exponent spot. So where that x is, it doesn't say anything about what that number can be. That's why you can pick negatives, you can pick positives, and you can pick 0. So in your calculator, you're going to plug in 2 to the negative 2, 2 to the negative 1, 2 to the 0, and so on, okay? So 2 to the negative 2 is 0.25. Okay, you could possibly put 0.3 because graphing a 0.25 is just kind of visually doing it, but I always write what it is to 2 places in the table, and then you're just going to estimate where that is when you're putting it on the graph. 2 to the negative 1 is 0.5. 2 to the 0 is 1 because anything to the 0 is 1. And then we get 2 to the first power, which is 2, and 2 to the second power, which is 4. You could do negative 3 and 3 as well if you wanted to, but I think doing at least 5 numbers is going to give you a pretty good idea of what it looks like. So let's put that on the graph. So my graph is pretty small, so mine won't look as good as yours probably. So negative 2, and then just a little bit above that. Negative 1 is 0.5. 0 is 1. 1 is 2. 2 is 4. Now mine kind of veered off a little bit. I don't like that. Just a second. Kind of goes like that. Now, if you did 3, 2 to the third power would be 8. So where it kind of veers up like that, it should be like up there about 8, which is right where that arrow is right there. So that's pretty good. So that's what an exponential equation looks like. So it's going to be a curve. Could they do something else with it where they move it somewhere? Absolutely. So, but this is kind of the general thing of what it's going to look like. Depending on the numbers they pick, if there's a plus number after it, that's going to move it like up or down. If it has something inside it, that's going to move it, right or left, and things like that. So we're going to look more with the translational part here in a second. Exponential growth as the value of x increases, the value of y increases as well. Something like, just an example of this one, if you put money into a savings account, you're adding money, and you should be getting interest on top of that, right? So it's getting bigger on both parts. That's kind of something that is an example of exponential growth. Or, you know, I was going to say stock is probably not a good example because that could get bigger, but it also could get smaller. So with that one, it's not really a good example of just it's continuously growing. It just depends on the rate that it's growing at. So stock, not an example, but just putting money into a CD or money into a savings account or something like that that does increase in value. It may not be very much, but it does increase. Exponential decay, when I think about that one, I think about science when they're trying to find out half-life, when something decays over time. That's kind of the one that kind of pops into my head. As the time gets bigger, the amount that's there gets smaller. Okay, so that's kind of what the decay one stands for. And then we have our exponential functions, and you kind of wrote this down, but you might want to add to it. So this equation, ab to the x, is the exact one we wrote on the previous page. It does explain what these numbers are again, but if you want to add to it, feel free to do that. So if it's an exponential growth question, a is going to be bigger than 0, so a is going to be a positive number. B is going to be bigger than 1. And then they talk about the growth factor. So it is getting bigger exponentially, and that's kind of what the growth factor is. Your B is going to be 1 plus R, and it's going to be written like a decimal. So how fast does it grow? Like, is it 5%? Is it 9%? Whatever. Exponential decay, your A is going to be positive, your B is going to be between 0 and 1. So when you guys are looking at equations like this, the way that you determine which one it is the B part. So you're going to look first, is B a number that's bigger than 1, or is it a number that's like a decimal or a fraction between 0 and 1? And that kind of determines what it looks like. Notice how the formula for the decay factor and the growth factor are really the same. But in the exponential decay question, the B is going to be like a negative number. Okay, so for exponential growth, the B is kind of a positive number. For the decay factor and the decay, it's going to be a negative number. Write these things down too with it, maybe underneath it. Because it kind of goes along with it, but it's not in these two groups. Another couple of things that they ask you about is what's the y-intercept, what's the domain, what are the asymptotes, and what is the range. So they ask you a lot of questions about these. And so we're going to write down what you would be looking for now. Does everybody have this part? So here's what I was just talking about. So underneath it, you might want to put y-intercept 0a. So basically that number at the beginning, the ab to the x, the a part is what the y-intercept is. The domain is going to be all real numbers. So what are the x's that you can put into these? You can put anything in there. The asymptote is y equals 0, and I'll go back to that initial graph that we did. It did have an asymptote at y equals 0, and then the range is also bigger than 0. And that would be if you plug in all the x's that you can, the range is always going to be bigger than 0. Basically, that asymptote line is where it comes really, really super close to, but doesn't go across. So if we go back to this one that we graphed, Notice right here, now I didn't put all this extra stuff on there, but this is kind of what you're thinking about. The asymptote line is right here. And that just means, again, the line that comes, your graph comes super close to, but doesn't go across. So it's never going to like cross it like this. Okay, it will come close to that. Your x is your domain, so it's going to keep going this way. So it's going to hit every x this side. It's going to keep going up, so eventually it hits all the x's on that side. That's why the domain is all real numbers. If you look at what the y values are, notice they don't go under this. So that's why it's y is greater than 0. And then your intercept this time is this point right here. So that is your y-intercept, and you should be able to do that. Also, that was your 0a. So remember on this one, our a was 1. So 0, 1 is your intercept. So everything that we just said works for this one. We just hadn't talked about it yet. Okay, so what do we look at without graphing these things and without having to calculate a whole lot of stuff? We're going to identify them as exponential growth or decay, and then what's the y-intercept. So just two of those pieces that we just talked about. So with the first thing, we're going to look at this number right here in both of these. That's going to be your y-intercept. So whatever that number is, it's 0, 12, and 0.25. So y-intercept for this one is 0, 12. Y-intercept for the next one would be 0.25. Okay, so that's the easiest part to do. The next part we're going to look at is this part. So what kind of numbers are those? So when you're looking at it, 0.95 is between 0 and 1, right? So that means this one is a decay question. So if you had to describe it or give a reason why, that's it right there. So everything in orange would be a reason for this one being a decay question. The other one is bigger than 1. So this is an exponential growth question. So the exponential growth question looks like that graph that we just did on that first one, 2 to the x. So it kind of looks like that. Now, sometimes they'll put these in words, so you kind of have to decipher word questions too. So you put $1,000 into a college savings account for 4 years. The account pays 5% interest annually. So when you look at this one, when you put money into a bank account, do you expect it to lose money when it's in the savings? No. So you're never going to lose money. You might not make quite as much. Now, this one is set for 5% annually, but what if it's real life and it's first at 5%, the next year goes to 4%? You're not really losing money, but you're not getting as much as you were at the beginning. So with this one, they have it just like this is a standard thing. So on this one, what I would write is growing, so exponential growth, because it is growing by 5% every year. So I'm really looking at that decimal, that percent interest that they're getting. And the y-intercept on this one is basically how much did you put in there at the beginning. Okay, so your y-intercept on this one, or where did you start kind of thing, is 0, $1,000. So still kind of easy to do. They don't really give you any other numbers, so you know, they shouldn't be too bad when you're looking at just deciding what kind it is. Okay, here's a formula that you probably should write down as well. So I'll pause it right here so you. So looking at the growth and decay formula, so notice it's the same formula for both, so that's a good thing because you wouldn't necessarily have to know right away which kind it was to pick the right formula, so that's good. A of t is the amount that is in there in this growth or decay question after t amount of time. So is it t years, is it t months, is it t days, what is it? So what is left kind of at the end of it? A is the initial amount. So if you think about science, if you start an experiment at the beginning, how much did you start with? Was it 50 grams? Was it, 100 liters? What was it? The rate of growth is kind of that parenthesis part. So if it's rate of growth, it'll be bigger than 0. If it's decay, it'll be less than 0. So when you put those numbers together, it will be a positive number if it's a growth. It'll be a negative number if it's a decay question. For the rate anyway, or the R. T is the number of time periods. So again, is it days, months, years, what is it? And each question there will be different. So we're going to do an investment question first. And we will kind of go back and forth looking at this formula so we know where to put stuff. So you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So when you were into high school, how much money would you have if it stayed consistent at 5%? So I'm going to jot down the formula just so we don't have to go back and forth as much. So I'm just going to kind of put numbers in as I read it. How much is in the account after 6 years? How much is there after 6 years? So A of 6. The small a is how much did you put in there, or how much did you start with? So in this one, it would be $1,000. The 1 just stays a 1. And then for the rate, I'm going to go back up here. I want you guys to add something to the directions up there. Your R will generally be a decimal number. Or when you put it in the formula, put it as decimal form. Decimal form in the formula. So in this case, the only decimal number that we actually have is that 5%. So instead of 5%, I'm going to put 0.05. So before I put it in here, that's what I need to change it to. And then T was how many years again? 6. So we're going to plug that 6 in there. Then all you have to do is grab your calculators, type it in. So you'll be just typing in the numbers on the right side. So try it. And here's the amount that I got. 1340.10. So the amount that's in there is your 1340.10. What if they said, how much did you gain in interest? Then what would you have to do? Yep, you would just subtract out the initial amount that you had. So let's put that in there too. So interest, just in case you have a question like this, 1340.10, subtract the initial amount out of there. So 340.10. So looks pretty good. The only thing that people tend to forget to do sometimes is change that number that's the R into a decimal form before you put it in there first. And you might have used this formula in other classes. You just may not have used it here yet. Okay, probably do this part as well. Sometimes they give you numbers that don't really give you what that R is. So the last one they gave us an R was 5%. And that was really super easy to just change to 0.05. But what do you do if they don't give you that R? You have to have numbers that can give you that, that R value. So we will do an example like that as well. So to find the growth factor, the Y really, in this case, the example that we're going to do is years. Year 2 minus year 1 divided by year 1. It will give us a decimal number or a percent. And then your B is going to be the 1 plus R like it was in the parentheses of the question. So even though it says it there, once you get the R value, you can still plug it in just like we did before. So problem 5, the table shows the world population of the Iberian lynx in 2003 and 2004. If this trend continues and the population is decreasing exponentially, how many lynx will there be in 2014? Use the general form of this equation. So I have kind of it all there. We have the formula already, so we're going to kind of use it as we go. Okay, so keep an eye on that one right there. If you do look in your book, it is basically a table that shows 2003 the population was 150, and in 2004 it was 120. So I'm going to jot that down off to the side. It wasn't a super huge table that you had to find a lot of things in there. So 2003 was 150, and 2004 was 120. So when you started looking, it was 150, and then it went down to 120. So it's getting smaller, and that's where this is going to be kind of an exponential decay kind of question. So I'm going to define some variables here. Many times you just kind of do them, but in order to see kind of where everything's coming from, I am going to define them this time. So for X, I'm going to define that as the number of years since it was started, which in this case is 2003. Okay, now even though these links have been around for a long time, when this person started documenting it was 2003. So that's why the X is the way it is. And then Y is going to be how many links are there. So the population of Iberian lynx. Now, this one doesn't give us any percentages, so this is where we're going to use that formula that we just wrote down. So to find that R value, year 1 is which one? So we need year 2 minus year 1. So year 1 was 2003, year 2 was 2004. So it's going to be 120 minus 150, and then you're going to divide by that year 1 again. And you get negative 0.2. So if you know the numbers are going down, you know that number is going to be negative. And it's basically what? A negative 30 over 150. And then just make that a smaller decimal. So now we are ready to put things into the formula. I'm going to use this one. I think the book simplifies this and does their B value and uses the middle one. So just in case you're wondering where they got stuff, I'm going to start where the formula is so you don't forget anything. Okay, so Y equals, what we started with was 150. So at year 1, there was 150 of these animals. In the parentheses, we have 1 plus a negative 0.2. Okay, now could you put that together right away? Yes. Okay, and then it's going to be taken to the, how many years between 2003 and 2014? 11. So that's where the 11 is going to come from. So this is 11, and that's what goes here. Now, the book goes through a big deal about how finding out how much you started with. I'm not really sure that's necessarily because And 2003, that's when we started, and the number was 150. So why go through all that just so that you can write it down on paper that it was 150? So when you look at that, they put 150 equals A times 0.8 to the 0. Not necessary. You can do it if you want to, but you're going to get exactly the number that they started with anyway. Okay, so just put it in there. Don't waste your time. So this one we're going to do y equals 150. This will be a 0.8 raised to the 11th. So you're going to calculate that on your calculator. You could do it with the parentheses if you want to. And you're going to get about 13. Now, I rounded to the whole number on this one because we are talking about animals, and we cannot have partial animals. I think it was at 13.4 or something. I don't remember. 12.8. Okay, so 12.8. So we rounded. And this is an approximate number because, of course, you know, you're looking at about how many are left, and it's about 13. So round if you're dealing with people or animals. People, animals. Now, in science, though, if you were talking about amounts of things that are left, could we do the 12.8 there? Yeah, absolutely. So it kind of depends on what you're talking about. So if it's like something you can measure, then keep the decimal. If it isn't, if it's people or things that you need, then get rid of it. Does that seem kind of easy? Kind of? It's a lot of formula stuff. I do want to go through one more. Let me see if it's something that we need. For your got it question number 5, it's really using the same model that we have. It says, what's the world population in 2020? So what if we change this to 2020 instead? We would take 2020, we would subtract 2003 from it, and we would have a different exponent right here is basically the only difference. Everything else would look exactly the same. So the other got it questions were related to what kind of model is it? Is it a growth model? Is it a decay model? What's the y-intercept? Things like that. So I think we should be okay there.